See the new topic, that is a current mirror circuit. Before we are going to start the current mirror circuit, okay, let me start the how to design the current source using active element. Okay, first we need to start to understand from the discrete components and integrated circuits. So whatever you studied in the earlier classes, that is your discrete, it's a discrete components, and this is an integrated circuit. Okay, so you can see here, when you go for the discrete way of making a circuit, the problem is the bulky in size, no entirely shock proof, more power consumption and less durability. When you go for the integrated circuits, like a it is made up of several components. Okay, they are made up of several components such as resistors and capacitors and diodes and transistors. They are built on single blocks or single chip of the semiconductor. Okay, the size will be very small, and the to to do the particular task all are integrated. Okay, so within the very small space I can combine many uh, many tasks can be accomplished. Okay, that too in like a normal resistors and capacitor functionalities are replaced. Okay, they replaced with your active biasing elements. Okay, so first we'll start with the how to design a constant current source. Okay, by using the MOSFET device. Okay, when you go for the normal current source, there are two types of current source we used to represent. One is your current source, another is a current sink. Okay, when you see the current source, like a current source will provide the current to the external circuit. This is a way of representing the current to the external circuit. When you go for the current sink, they receive the current from the external circuit. Okay, for both the cases, I am going to consider the current source for our entire discussion. Okay, so the current source is nothing but your current will be constant with respect to the changes of your voltage. Okay, this functionality I want to design the same functionality with your active devices. Okay, that means your MOSFET have to give the same functionality. How? That we are going to discuss now. Okay, see, now let me start with the basic circuit. So this is a normal current source circuit that we are expected. Okay, now I'll take a MOSFET. In the MOSFET, you know, this is your gate and this is your drain and source, right? What is the basic equation for the MOSFET? That is the master equation for the drain current. ID equal to Kn VGS minus VTN whole square. Here, this drain current is dependent to this VGS. Okay, another thing, to make your transistor to work in saturation region, this is a saturation region, this is a ohmic region, and this is a cutoff region. So to make this transistor to work in the saturation region, the condition is the VDS should be greater than or equal to VGS minus VTN. Right, this is a basic condition you know. The other name for this is override voltage. Okay, don't confuse. Just to remember, the other name for VGS minus VTN is nothing but a override voltage. In some book it was specified like this. So we can take it as a VDS saturation, that is a VDS saturation is greater than or equal to VGS minus VTN to move to the saturation condition. So during that condition you can see the current was almost constant, not completely, you have some slope. Okay, you have some slope. Okay, so our work is like we want to reduce the slope as much possible. Okay, so like you can see the id is a function of vgs, that is the first thing. Another one is the MOSFET to go to the saturation region, you want a minimum amount of voltage. That minimum amount of voltage is your VGS minus VTN, right? Another thing, you know, the gate current is almost zero, right? So in the MOSFET, okay. So there is a two case you want to consider in the when you studying a MOSFET with channel length modulation, another is a without channel length modulation. Okay, so the ideal case is without channel length modulation, but realistic in the real system you have a channel length modulation. Okay, both you want to consider and you want to study. Okay, now condition is how to design the constant current source. Okay, so you can see here in the MOSFET, this place you can see the current is almost constant. The changes of id with respect to vd is very less. Okay, so this is a part we are expected. Okay, we know that normal current source is something like this, right? So we can see a constant current here, also you can see the constant current, same function almost. So that means I want to make a MOSFET to work in the saturation region, so that I can bring the functionality of a constant current source, that is a resistant functionality, by using your active elements. Okay, how? The thing is, I want to short your gate and drain. Okay, so how we can do is, I want to short the gate and drain. Okay, if you short a gate and drain, what happen? If you short a gate and drain, okay, so gate is your VGS, VDS will be equal to VGS. Okay, you know that like a drain current, and VGS. So it is an enhancement MOSFET, right? In the enhancement MOSFET, you want to give minimum amount of voltage to create the channel. Until that, the channel will not be created and current also zero, right? So that we are taking as a threshold voltage, right? So you can see this is a region at which the your channel is not created and it is trying to create. So once your VGS equal to your threshold voltage, from VGS only you are taking. Okay, so once your VGS is equal to threshold voltage, the channel is created, then only current is starting to produce. Okay, this is one idea you keep in mind. The another thing is your VDS is equal to VGS. Okay, so these are two things. Now when you write when VDS is equal to VGS, because your this element you are shorted, that's why you are writing like that, right? VDS is equal to VGS. So obviously you want to know like a VDS should be greater than VGS. Why? Because the threshold voltage was taking from your VGS only. That is a minimum amount of voltage to create a channel. So obviously VGS minus VTN will come, right? So that means your drain saturation voltage will be greater than your gate source voltage, obviously. So that means when you short your drain and gate, your MOSFET is forcing to work in the saturation region. Okay, so that you are get the functionality of the current source using the active elements. So you can replace your resistor. Okay, to usually will be giving a connecting some resistor to generate the current source, right? So that can be replaced with your active devices. Okay, so I'm repeating again the first task. You know the drain current is determining after the threshold voltage, after the generating a channel only. With respect to the change of VDS, the ID is changing, right? So the second thing is here both gate and drain are shorted. So obviously you should need to know with this idea the VDS should be greater than or equal greater than VGS minus VTN. Okay, that when you say in VDS is greater than in VGS minus VTN, it is forcing to work in saturation region. You know that what is the condition for saturation region? VDS is greater than or equal to VGS minus VTN. So our task is accomplished, right? So this is a way how your MOSFET is working as a constant current source. So this idea only we are going to use for your current mirror circuit. I hope you understand. Right. Now we will go for current mirror concept. What you learned is how to design the constant current source with the MOSFET devices. I hope it was clear. Now we go for the current mirror circuit. Okay, in the current mirror circuit, what do you mean by current mirror? Very simple. It is copying the current to the end terminals. Okay, why you want to copy? That is a question. See, when you design the chip, or microprocessor or any fundamental blocks, you will be having the thousands of amplifiers. Okay, you will be having the thousands of amplifiers. Okay, it is very difficult to provide the biasing to the individual thousand circuit with the discrete components. Obviously, you know why that is the reason why you are going for the uh, like from your discrete element to the active elements. Okay, so what you are going for, what current mirror is doing is, I'm going to generate on constant current source. Okay, this constant current source is like a biasing. It's a biasing actually. Okay, their functionality of resistor was replaced by your constant current source, and I'm going to replicate in the n number of your amplifier circuits. See, I'm going to generate only at one terminal, right, and going to copy at the n number of circuits. Basically the current mirror is a, you know, it's a like a DC current source, and it is going to replicate in the several independent circuit branches. So that is a very popular concept in the integrated circuits. Okay, especially we used to this concept in the analog circuit design. Okay, so the current source is widely used as an active load. Okay, as an active load to improve the amplifier gain. So we can design this current source using active element, that is a BJT, MOSFET, anything, but here we are going to focus only on the MOSFET. Okay, so the current mirror is one of the basic building block in the signal processing circuits. Okay, so I said clearly the current mirror is an analog circuits. So it going to generate some constant current, and this generate, okay, but it is copying in the n number of points. Okay, so I can write like a I copy equal to IREF in the subscript, I copy equal to IREF. Okay, or it could be like a either multiple or fraction of your reference current. So I copy equal to n into IREF, or I copy equal to 1 by n times of your IREF. Okay, the very simple idea is I'm going to generate the constant current source that is going to replicate in a n number of places. So that is a concept that we are developing with the MOSFET. Okay, okay, this is a normal current source circuit. Here you can see here I am giving a supply, and this is a some constant current. Okay, constant current I am providing. Okay, this is your MOSFET element, and this is your another MOSFET element. Here what you want to understand here is, here gate and drain are shorted, so gate current is 0, not 0, but approximately we are taking 0, you know, as you discussed the reason in previous lecture also. It current will be in terms of like nanoamps or picoamps, so we will not consider. Okay, approximately Ig is 0, right? So Ig will be 0. Okay, so gate and drain are shorted. If gate and drain are shorted, we used to say as a diode connected load, or we know that it is acting as a constant current source. We explained the reason also, right? So here you can see always this M1 transistor will be in the saturation region. Always the M1 saturation will be in the saturation region because the drain and gate are shorted. Okay, so here I am giving the some reference current. Okay, I am giving the reference current. So the same current will come in the drain current also, because the no, you know that the no current will go to the gate terminal. Okay, so IREF is equal to ID1, right? IREF is equal to ID1, you want to understand. Okay, now thing is, this is biased. Your MOSFET was biased with the VGS, right? Same VGS, that is VGS1, it is biased. Same VGS1 I am biasing to the M2 also, M2 also, so that I am taking as a VGS2. So you know that VGS1 is equal to VGS2, so VGS2 equal to VGS. Okay, so thing is, you will be getting the same current, that is a copy current here. So I naught is equal to IREF, that is our concept. Okay, so for that we need to consider first without channel length modulation and with channel length modulation. First we will start with the without channel length modulation, that is a channel length modulation parameter is 0. I am taking as a without channel length modulation proceeding. Okay, so here you want to understand, here is M1 is connected in the back to back, so it is a diode connected load, so forcing this transistor to act as a constant current source. Okay, and here already we are providing the some constant current source. Okay, that is a reference current, it may be like a some milliamps or 1 milliamps or something. Okay, so we know that IREF is equal to ID1. Okay, so here something, the circuit, analog circuits are connected. Analog circuits are connected in the top. Okay, so finally I naught is equal to IREF. How? Okay, without channel length modulation. Okay, that is the first thing I am taking. Okay, okay, very important. Okay, so IREF equal to ID1, I said clearly because same current will come here. Because the gate current is 0, so IREF is equal to ID1. IREF equal to ID1, right? IREF equal to ID1. So IREF equal to ID1. What is the equation for ID1? 1 by 2 K dash N W by L. The subscript you have 1 because you are writing for M1 transistor, VGS minus VTN whole square. So that whole function, you know that whole function I can write it as a Kn. Okay, Kn. Okay, so Kn1. What is the meaning of 1? Because I am writing for transistor 1. So this whole function, that is your or K dash N 1 by 2 W by L, that whole function I am writing as a Kn. So 1 is for transistor 1. Okay, so VGS minus VTN whole square. Now I am rewriting this equation like IREF, you bring this Kn down. Okay, so bring this Kn and K dash N down and it becomes IREF divided by K dash N equal to VGS minus VTN whole square. And I am bringing this square to left side. So it becomes square root. Right. So what actually you will be having IREF divided by K dash N. So I can bring this VTN to the left side. So VTN equal to VGS. So this is a very important formula, will be used for the numerical. So what you learned is the VGS can be written as VT1 plus square root of IREF divided by KN1 square root of. Okay, so very important formula to be used in the numerical. Okay, so another formula is a IREF. I can write IREF or ID1 in another way. How means V plus minus this drop divided by this. You consider this resistor like you have some here they given the constant current source, right? You consider there is a resistor here. Okay, consider. So that means you have some current, right? And this current some current, then that current, how you can find? V plus minus this V minus, sorry, minus this VGS divided by this R resistance R. So repeating again, I want to see here, you just consider you have a resistor. I want to find what is the current, that is a V plus minus VGS divided by here R. With that I can find what is your current across this resistor. Okay, so what you will get? IRF equal to VDD minus VGS by R. Okay, so that is why it was written like this. So this will be very useful when you solving the numericals. Actually, you know that like a basic current equation, that is ID equal to Kn VGS minus VTN whole square. So that formula will be compared with this one to find what is your VGS voltage. Okay, that will be very useful. Okay, now we know that already I said clearly the same VGS only I am giving to the M2. That means M2 was driven by M1. Okay, the VGS 1 voltage was even same to the VGS2. That means M2 was driven by M1. Okay, so your I0 current will be obviously, no doubt, 1 by 2 K dash N W by L2 VGS minus VTN whole square. So that whole function can be written as a Kn2 VGS minus VTN whole 2. Okay, so already we learned like a VGS is nothing but a VTN1 plus square root of IRF plus Kn. Now I want to substitute here. So another thing, so when you are designing the current mirror, we want to consider the both are matched. Unless both are not matched, I can't design the current mirror circuit. Okay, your mu COX, your threshold voltage, your K dash N parameter, your width and length, everything to be matched. Okay, that depends on the design. Okay, if it is matched, you will be getting the perfect current mirror. Otherwise, it will change based on the parameters. Okay, the first already I said what I am going to proceed here. I have substituted this VGS here, so that your I not equal to ID will be changing with respect to the next update or equation. You can see here I have substituted that VGS. This whole term is your VGS. You can see the previous slide. Okay, so I naught equal to Kn2 square root of IRF divided by Kn plus Vn1 minus Vn2. Okay, now I said clearly all are matched parameters. Okay, so your Kn1 and Kn2 all are same, then your Vtn and Vtn2 all are same. That means everything will be cancelled, right? Everything will be cancelled from this equation. Only I am taking an initial assumption like a W by ratio is not equal, not initially I am taking. Okay, so that means you remaining all parameters will be cancelled and you will be having by W by L parameter alone. W by L and W by L for this is for M2 transistor and this is for M1 transistor. Okay, now in second assumption I am bringing this also same. Okay, this also same, so both will get cancelled, so I naught is equal to IRF. Okay, so from already said both are identical transistors, so I have considered VTN threshold voltage equal to VTN2 and Kn1 equal to Kn2. With that it was written like that. So in the second assumption I am bringing your W by L ratio also constant, so I naught is equal to IRF. Okay, so another thing, mostly in the MOSFET length only will be modified. So you can see this is your length, right? This is the length of the channel. You consider this a channel. Okay, so that means in between your this is your source and this is your drain, right? In between your channel, so this is your length and this is your width. So best method is like a changing a length. Okay, so the width by length ratio, it's a very important parameter in the current equation. So based on the width and length parameter only the current was determined. Okay, so final thing is, then the current mirror circuit without channel length modulation, the parameters are identical, all the parameters are identical, lambda equal to 0 such that I naught is equal to I ref. So I am copying the current of I reference to the I naught. So if you consider like I am giving 1 milliamp, so I naught also 1 milliamp. So I am generated at one point and replicated into n number of terminals. Okay.